Okay, so this problem is asking us to look at the reaction where we have N2O4, which is a gas, being converted into 2NO2, which is also a gas, and it's asking us for the correct equilibrium constant for this equation. So for this one, I am assuming that they're asking for Kc since the reactions are in concentration brackets as opposed to being in partial pressures. So whenever I get a equilibrium constant, a Keq or a Kc or a Kp, whatever, it's going to be equal to the concentration of the products, so it's final over initial. And the concentrations are going to be raised to their stoichiometric coefficients. So in this case, it's going to be the concentration of NO2 raised to the second power over the concentration of N2O4, so that's products over reactants, which is going to be option B. Same thing over here, so we're being asked to find the correct equilibrium constant expression. Again, my units are in concentration. So remember, if I had anything that was a solid, that wouldn't be part of my equilibrium concentration expression, but in this case I don't have anything like that. So again, my Keq is going to be equal to the concentration of products, which is CH3OH, which we now know is methanol. Divided by the concentration of CO2 raised to the first power, because that's its coefficient, times the concentration of H2 raised to its coefficient. So this is going to be option number E. Here, we're given an equilibrium concentration for one equation. We're told that the Keq is 0.112 at 700 degrees Celsius, and then we're being asked to find the Keq of another reaction at the same temperature. So with these kinds of questions, I need to figure out what is being done to the equation. So how is this equation different than this equation? If you look, SO2 is on this side, so it's a reactant on this side, whereas it is on the products over here. Oxygen is a reactant on this one, oxygen is a product over here, and the product is the reactant over here. So basically they just took this equation and they flipped it. So since they flipped it, if I were to look at the equilibrium constant, this would be SO3 over the concentration of SO2 times the concentration of O2 raised to the 1/2. The equilibrium, and I know that this is equal to 0.112 because they told me that. This one is literally the opposite, right? So it's the exact same equation except it's been flipped. So if I flip the equation, I would also flip the equilibrium expression. So if I flip the equilibrium expression, it's going to flip this, which means instead of it being 0.112, it's going to be 1 over 0.112 equals the Keq for this equation. So if I do 1 divided by 0.112, it's going to be 0.893, which is option D. So whatever I do to the expression to get this one, I do the same thing to the equilibrium constant to get the new Keq. So in this one, I flipped it, so I would flip the Keq by doing 1 over the Keq for the first one, which gives me 8, I'm sorry, it's not 0.893, it's 8.93. I don't know what's wrong with me. I keep drawing a 0. I'm saying the right thing, I'm just writing the numbers. 8.93, which is option D. Alright, so this is a special type of equilibrium problem with acids and bases where I'm being given the pH of a solution of a weak acid, and I'm told what the pH is, and I'm being asked to find the Ka. So Ka is the dissociation constant of an acid. So in this case, my acid is HBRO minus, and it's going to dissociate into H plus and BRO minus, which means my Ka is going to be equal to H plus times BRO minus over the concentration of HBRO. So my acid dissociation constant is always going to be the proton and the conjugate base over the undissociated acid. So remember, with weak acids, we consider the concentration of protons, so basically the dissociation, to be very, 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 very small. So for this equation, I'm going to need to make an ice table. So I'm going to have, for each thing, so I have my undissociated acid, HBRO. I have my H plus, and I have my BRO minus, and I'm going to need to know my initial, my change, and my equilibrium. Okay, so HBRO, the initial concentration of it, is what I'm given. So that's this 0.55 molar, because what I'm starting with is 100% hydrobromic acid. So my initial concentration of HBRO is 0.55 molar, and because this is a weak acid and I'm assuming that it is associating very, very little, I'm going to say that the change is basically 0, which means that at equilibrium I still have basically 0.55 molar hydrobromic acid. To get the concentration of the protons, I'm going to use the pH. So pH is equal to the what did it say? 4.48. So negative log of the proton concentration is pH. How do I get from proton to the concentration of H plus? I do 10 raised to the negative pH is equal to the concentration of protons. So in this case, I would do 10 to the negative 4.48. So let me do that real quick. Okay, so when I put that into my calculator, I found that 10 to the negative 4.48 was 3.31. So the concentration of protons basically is 3.31 times 10 to the negative 10 to the negative 5. So very small dissociation constant. So if that's the concentration of H plus, that's also going to be the concentration of BRO minus. So 3.31 times 10 to the negative 5. So you can see now why we consider this to be negligible. So this, I'm sorry, oops. Sorry, this should go down here. These should be 0 and 0. And they increase when they dissociate to 3.31 times 10 to the negative 5. My bad. Alright, so if it started at 0 because it initially was 100% this and it increased by this much at equilibrium, this is going to be 3.31 E negative 5, and this is going to be 3.31 E negative 5. So now that I have all my information, I can plug it into my ICE table, and I know that my Ka is going to be equal to 3.31 E negative 5 times 3.31 E negative 5 divided by my 0.55 molar. So it's, again, the proton, the BRO minus, so the conjugate base, divided by the undissociated acid. So let's plug that into our calculator and figure out what that gives us. Alright, so when I plug this into my calculator, I got 1.99 and a bunch of other stuff, E negative 9, and the closest answer to that would be A, 2.0 times 10 to the negative 9. So that is the value of the Ka, or the dissociation constant, for the acid.